All right. Yeah. So we're gonna start chapter 7 today, but I'm gonna quickly go through. I'm not going through. Chapter 10 is on radicals, and I know I didn't have you guys read this. Sort of made the decision to do this. Not quite last minute, but this morning. So if you look at what I say we're going to do, we get through 11. So basically 1 through 11 and 14 and 15. And 11 is always by agreement amongst the faculty who teach organic. 11 is always sort of, we'll try to do as much there as we can, but if you don't get, that's where we start, where you guys will start in Orgo 2. So 10 is useful. There's one really useful reaction in it, and then there's a lot more discussion, and there's a lot more you can do with radicals. We also put polymerization there. You guys have seen polymerization in lab. I mean, it wasn't a real in-depth treatment, but everybody made some plexiglass in the lab using radicals. So I figured today I could just sort of do this one reaction that we really need to do, talk about radicals in general a little bit, and then the rest of the semester could be chapter 7 if it needed to. So this reaction is just a radical would be called a radical halogenation. All right, so you're basically going to replace an H with a chlorine. And the two things you need to do this are chlorine gas, Cl2, and light. All right, so light is a lot of radical reactions are initiated by light. And if you think about that, to get a radical to form, right, you need to homolytically cleave this bond. All right, and I've said this a number of times in here. The mechanism for a radical reaction, you can draw curved arrow mechanisms for radical reactions. But the rules don't really follow the rules you guys have started studying. So I generally don't like introducing radical mechanisms at this point in your development because you're still trying to get a handle on ionic mechanisms where a curved arrow represents 2 electrons and it's like a circuit and everything sort of flows. In radical reactions, you've got 1 electrons doing things. All right, so there you can have arrows going different ways. So like in a homolytic cleavage, we would represent this as an arrow with a single barb here, thus, representing 1 electron, and another arrow going from the bond, also with a single barb. So basically, for the 2 shared electrons, 1 electron goes to X, 1 electron goes to Y, and you get what is called a radical. So a radical is going to be any molecule or atom that has an unpaired electron. Okay, so both X and Y here, and they're going to be, if they were neutral here, they're going to be neutral here. Because remember, when we do formal charge, X counts half of the shared electrons with Y, Y counts half of the shared electrons with X. If you put 1 of the 2 electrons on each, the math works out the same. Okay, so the reason these radical reactions often use light, or why light-induced reactions, photochemical reactions, often involve radicals. If you think about what has to happen when a molecule absorbs a photon of light, right, a bonding electron is promoted to an antibonding orbital. Like in effect, you've taken 1 of the 2 bonding electrons out of the bonding orbital and separated it from its partner. All right, and that often results in molecules that have unpaired electrons. You can also do this reaction with bromine. All right, and if you dig into chapter 10, I know nobody's read that yet. Bromination is selective, chlorination is not. So that top reaction, this top reaction is really only useful if you're chlorinating a symmetrical molecule, right? If I take cyclohexane, every one of those hydrogens is equivalent. So it doesn't matter which one I pull off and put the chlorine on. In the bottom one, I've got some methyl, I've got 3 methyl positions, I've got a secondary carbon, and I've got a tertiary carbon. If I did this reaction with chlorine, I'd get chlorine here and there, I'd get chlorine there, I'd get chlorine there, I'd get chlorine there, I'd get chlorine sort of in all of those, and it would be a mess. So if you use bromine, the bromine selectively goes on the more stable, the carbon that would form the most stable radical. And at this point, it'd be fair for you to say, well, I have no idea what makes for a stable radical. Fortunately, you do know what makes for a stable cation. All right, so you should have had this from the last sequence. Tertiary cation, a carbon with a vacant p orbital that's bonded to 3 other groups is more stable than a secondary carbocation. And that's more stable than a primary. And really, essentially, methyl radicals don't form. Well, radical stability goes right along with this. The difference is a little smaller. Methyl radicals absolutely form. Primary radicals aren't that bad. But tertiary radicals are more stable than secondaries, more stable than primary. It's more stable than methyl. Same thing with the cations. If you can delocalize the radical, it's more stable. So delocalization will increase stability, and then the last thing I'll stay on this, and this is sort of all right, so for anion, radical, and cation, delocalization adds stability. Cation stability, right, if you remember the explanation, this cation gets stabilized by bonding electrons adjacent to it, right? So if we have right, so we have a CH bond here, and that can interact with that vacant p orbital, stabilize the vacant p orbital a little bit, right? It's not a huge, that's not a bonding interaction in any way, but it helps stabilize. The carbon-centered radical here is more like a cation than an anion. The formal charge is neutral, but that carbon doesn't have an octet, so it's electron deficient. Right, so you know, when I was 15, I didn't have much money. Society looked at me and said, you're not supposed to have much money. You're fine. I still didn't have any money. I wanted money. Right? So that carbon, even though we say it's neutral, would still like some electrons. And so it's like a cation. Anything that adds electrons to that radical center stabilizes it. For the same reason, if those groups are adding electrons, right, that's going to destabilize an excess of electrons. There my financial analogy fails. right? If I have a lot of money, I would still like more money. So just this anion having electrons already, though, it's unstable because it's got an excess of electrons. Things are trying to give it electrons. That's destabilizing. Okay, so having this, you definitely need to have this down for Chapter 7. This is going to be really important in stuff we're about to do. This is kind of moderately important. I would like you to know that radical stability charts with cation stability. Next semester, you're going to need to have that reverse, okay? And so that's pretty much, I'm going to go through the mechanism here. Like I said, you guys don't have to know this mechanism, all right? Radical mechanisms, though, radical mechanisms are kind of interesting. You might have seen them in Gen Chem. And there are, I'm not minimizing it because it's not important and because it's not common in chemistry. I'm minimizing it because this semester in organic chemistry really kind of focuses on ionic mechanisms, Lewis acid, Lewis base chemistry. And radicals don't fit that. So we have, in radical chemistry, we have an initiation step, right? You're almost never going to have ground state radicals, like a radical molecule that you can put in a bottle and just pull out. We have that for ions, right? So I can, sodium NaNH2, you guys have seen that, right? Sodium hydroxide, that's a better example that you've actually used. Sodium plus, OH minus, I've got cations, I've got anions, it's up in a bottle. I can take it out, I can weigh it out, pour it in. You can't do that with radicals, okay? I can't just start with a bunch of radicals. So you have to initiate the reaction. The initiation step is going to go from no radicals to radicals. And then we get what are called propagation steps. If I don't stop myself, I put like 19 A's in that. And so here, for this reaction, and again, I am not going to ask you to draw a mechanism. The bromine's going to take this hydrogen. It's going to look like an acid-base reaction, but it's not. All right, so the bromine to the H is going to come off not as a proton, it's going to come off as a hydrogen atom. So H dot and Br dot are going to combine, and that's going to leave one electron on this carbon. We make HBr. And right, so in a propagation step, you've got radicals, and you get radicals. And then the second step here, this radical is going to react with bromine. So we make a CBr bond. We break the Br-Br bond. That gives us our product, but we get another radical. Right? And then that bromine, this bromine atom can come back and do it all over again. So it's a chain process, right? One initiation step can give you tens of thousands of product molecules. Again, that's pretty hard to pull off in ionic chemistry. And it's also a reason that radical chemistry is used so often in polymer chemistry, right? If I want to think back to your plexiglass reaction, you had a methyl methacrylate react with a methyl methacrylate, and then that reacted with a methyl methacrylate. A chain process is ideal for that, right? I get one initiation step, the initiator reacts with a methyl methacrylate, and then that thing reacts with like 100,000 more methyl methacrylates. And I get this giant molecule that I can make a desk out of. All right? We really give kind of short shrift to polymers in this class. The organic chemistry, and I think it's because of Wake's, there's a huge number of pre-meds in this room. Those of you who are not pre-meds are kind of bio-leaning, which is fine. That's great. A huge chunk of organic chemistry is biochemistry. But there's a lot that has really almost zero to do with biology. Okay, humans pump, I don't know what the number is, I should look it up, some unsustainable amount of carbon, decayed organic matter out of the earth every year. We burn it to move around, but we make a lot. Like if you just look around at this room, there's a little bit of wood over here, there's a little bit of metal. Pretty much everything else is made of dead dinosaur, right? In a very long process. But this polymerization step is the last process to happen there. It's a hugely important for consideration of the environment, for our economy, for just our daily life. And I'm pretty much wrapping it up here. So we're going to go back to stuff that will be more important for the biochemistry. So the last step, right, this is your propagation step. Like I said, you're never really going to end up with radicals as a product. All right, the products are going to be closed, we call them closed shell molecules. A closed shell molecule is any molecule or atom where all the electrons are paired. It could be an ion, but if there's an electron, it's got a pair, right? So we have a lone pair, we have a bonding pair, there's no just single electrons floating around. And you know, these could be, the simplest one in this reaction would be, just going back to Br2. You can imagine the carbon-centered radicals reacting with each other to make a carbon-carbon bond. They can disproportionate. So these are always formed as a pair, right? If one of these radicals takes a hydrogen from the other molecule, you'd get a fully reduced version and an unsaturated version. So this is called disproportionation, which is a word you might just probe. Anyway, it's an English word. You can look it up. And then the last is and again, this is another hugely important. This actually is important in biochemistry, and I'm going to leave it here, and I hate that. But if I talk about it, given my professional interest, I will spend the next 6 weeks talking about it. So I've said that radicals, you can't isolate a radical. That very few molecules, very few stable molecules are open shell. That is, have an unpaired electron. You guys know this. I remember at the beginning of the semester, I had this resonance structure assignment. A whole bunch of people were like, yeah, having just the dots there, that can't happen because electrons can't be that way. And the reason you got taught that or internalized it is because most molecules don't do that, right? Having unpaired electrons in molecules, those molecules are really reactive. So they're not something stable that you're going to interact with. There is one enormous exception to that. How did I make this radical in the lower right over here? What did the carbon-centered radical react with to make this over here, that molecule? Yes. I was just about to really be a smartass and tell you all you had to hold your breath until you thought of it. So O2. And this reaction, so oxygen, everybody wants to draw oxygen this way. Okay, everybody wants, I've wanted to draw it that way still occasionally because it looks nice. It's all closed shell. There's no weird single electron. There are no charges. Oxygen makes 2 bonds. Oxygen's supposed to have 2 bonds. If you dig into the quantum mechanics, and this was a real vindication for quantum mechanics over Lewis structure. So in the early 20th century, everybody who liked Lewis structures was like, this has got to be the way oxygen is. All right, the physicists were like, no, that's not how oxygen is. Oxygen, in fact, looks like this. No, what am I doing? That second bond is not there. In molecular oxygen that we're all breathing right now, that we have to stay alive, the two oxygens have a single bond, and these two electrons, and then each oxygen has one unpaired electron. Moreover, we can go farther than that. You remember electron spin, right? Spins can be paired. In molecular oxygen, those two electrons those spins are unpaired. So in chemistry, as shorthand, if we want to say spins are unpaired, we draw them the same direction, either both up or both down. Doesn't mean they're both up. It means they're unpaired. They could both be up. They could both be down. One could be up. One could be down. When you hear that phrase, paired spins, it means if you know the spin of one, you know the spin of the other, right? So if I look at a lone pair, you probably think we call them a pair because there's two of them. Pretty obvious thing to do. We actually mean those spins are paired. So like to be in the same orbital, if one of them is spin plus half, the other one has to be spin minus half, or up and down. So in oxygen, these spins are unpaired. That means they really do. Molecular oxygen reacts like it's a diradical. Right? Molecular oxygen, as you know, is an incredibly reactive molecule. And if you leave basically anything out exposed to oxygen, it oxidizes. And yet we have to have it to live, right? We have to breathe it in, and we have to do chemistry with it. And so we really are taking advantage of the fact that that molecule, the O2, is extremely reactive. That's what drives us every day. It also, in the long run, has a lot of really nasty effects, right? As I said, and everybody sort of nodded, right? If I take let's say I take a steak and I just leave it out. Let's say I leave it out in my house at 72 degrees Fahrenheit for a week. Do you guys want to eat that steak? No, right. Why? Let's say I leave it in my house, except I've got a special house and I can evacuate my house. I mean, I can leave it, I can turn my house into space. Right? There's no O2, no N2, nothing's in there. Now would you eat that steak? You should, be fine. Right? So organic matter exposed to oxygen oxidizes and decomposes. Right? So I don't want to be a downer today. It's a beautiful spring day. We're at the tail end of a pandemic. But you guys and me are organic matter. Right? We're exposed to oxygen constantly. We have to be. Right? You can't go more than a couple of minutes. Well, the average person can't go more than a couple of minutes without O2. And what that means is an awful lot of the biochemical machinery in your body is devoted to making sure that oxygen doesn't just decompose you. And in the long run, so this is, if you guys have probably all heard this, like the first person to live to 150 has been born. That's a popular, not necessarily valid statement. But the idea is modern medicine is going to continue to push the boundaries of how long people can live. That one's going to be the one. If you solve everything, if you solve every disease, you can cure anything, ultimately, you're going to run into the fact that your brain's going to oxidize away. All right, so you have to beat that. If you can beat that, you're immortal. So it's easy. If you do that, you get an A. If you can give me that secret, I will give you an A in this class. Okay, so like I said, not a downer, but you've heard about antioxidants. That's what it's referring to. Okay, to make us function, we have to use O2 to oxidize organic compounds, and that is an inherently dangerous thing to do. So you have to balance that somehow. And I mean, seriously, like you guys all hopefully will live 80, 90 years. Maybe I will too. Like that is. I always hesitate in here to use the word miracle, because it's not. There's lots of explanations for that, lots of good science. But it's amazing. It's incredible that if you looked at the sum collective fragility of a human body and said, yeah, it's going to walk around in 20% O2 for 90 years, like, it's just unbelievable. Don't think about it too much, especially as you go down. Like, that can be a spiral as you go into finals. Okay, so that's chapter 10. Hope that got recorded. Basically what you don't need, I'm never going to ask you about a mechanism. Oh, I need to write one more word down here. These steps down here are termination steps, which you probably knew. And actually, on the heels of what I've been talking about is a bad way of, that's a bad word. So, termination steps, you've got radicals going to not radicals. And this is kind of, there's kind of two things I'd like you to get out of this. One is the reactions that we do, all right? So Cl2, Br2 plus light. And light here is H nu. That's a scribble. It's supposed to be a nu, the Greek letter nu. Planck's constant times the frequency, that's the energy of a photon. All right? So if you guys would rather just write light here, you can do that. All right, so if I take Cl2 or Br2 and I shine light on it, I'm going to end up replacing an H with either a Cl, if I use Cl2, or the H that would make the most stable radical, like pulling it off, leaving a radical there. I'm going to replace that H with a Br. All right, and that's going to be important in the next bit. And then also this board has a lot of cool stuff on it. Radical mechanisms, again, I'm not going to ask you to draw those mechanisms, but you should be familiar with initiation, propagation, and termination. We're going to initiate reactions by taking molecules that aren't radicals, turning them into radicals. Propagation steps are the radicals do in chemistry. So a radical is going to react with something, give a product, and a radical. And in the termination steps, we go from radicals to not radicals. It's really important as you do these reactions not to have O2 around. So in a lot of the chemistry we do, right, if we have to use a super strong base, if I need to use NH2 minus, I can't have water in there, right? Because the NH2 minus will just take a proton from water. In a radical reaction, water's fine. The OH bond in water is really strong. But O2 can't be present. Because if I make a bunch of radicals in O2, the O2 is going to oxidize those radicals. And I doubt this turns into any points for anybody in here. But that's a personal, like, you should, in any chemical field, you should know that O2 is a diradical and super reactive. All right. So, chapter 10. I figured it was only fair for you guys. I did all of chapter 9 on Tuesday. All right, so if you haven't watched the video yet, or you weren't here, everything we're doing in chapter 9 was in Tuesday's class. It's recorded. That's alkynes. That's alkynes, carbon-carbon triple bonds, basically doing the same chemistry that alkenes, carbon-carbon double bonds do. All right, and you guys know that from the exam, for your preparation for the exam. Figured it was only fair to give you guys your own one-day chapter as well. 29 minutes, that's not bad. All right, so like I said, now we're going to go back to chapter 7. And chapter 7 is going to occupy most of the, if not all the rest of the semester, most of the rest of the semester. And then we'll try to sum it up with chapter 11 a little bit at the end. So chapter 7 are the reactions of alkyl halides. And that's one reason I say this is kind of a nice segue in here, right? So chapter 7 will deal with molecules that look like this, where you have an sp3 carbon halide bond. So the important thing in this molecule is the sp3 carbon chloride bond, or not leaving group, not yet. X, right? So sp3 carbon bonded to a halogen. And again, the halogens in this case, in chapter 7, the halogens are going to be chloride, bromide, and iodide. So we're not going to look at fluoride much. And we would say from terminology here, this molecule is going to be a secondary chloride. All right, so the chlorine is bonded to a secondary carbon. You're sort of looking at what are the other things. Besides the halogen, how many other carbons are there? If there are 2, it's a secondary. If there are 3, it's a tertiary. If there's 1, it's a primary. All right, so this is a tertiary bromide. And that's going to be important to distinguish. All right, so the chemistry of a primary halide is going to be a little different than the chemistry of a tertiary halide. What else is important here? Oh, yeah. And also, I can't really underscore this enough. All the stuff we do in chapter 7 is going to involve sp3 carbons bonded to the halogens. So all the reactions we talk about are not going to involve sp2 or sp carbons bonded to those halogens. All right, so chapter 7. Let's do a little review. So draw the product of that reaction and the mechanism for that reaction. And yeah, it kind of looks like the same stuff over here, but this is not a radical mechanism. This is a ionic mechanism. Okay, so I've filled that in. I've drawn the product, I've drawn the intermediate, drawn the curved arrows, right? So the pi electrons, so I guess I've written chapter 7 here just as an indication that we have now started chapter 7. All right? This reaction comes from chapter 8. The pi electrons are basic. They grab the proton, they break the HBr bond. That's going to give you a carbocation. Again, the carbocation that forms is going to be the most stable carbocation. So we get the tertiary cation, and then we've got this Br minus floating there. The Br minus can use its electrons to make a bond to the carbocation. Everybody's got a full octet again. Curved arrow starts with the electrons on the bromine, goes to the carbon that's getting the bond. Same thing up here. Curved arrow starts with the pi electrons, goes to the H. Arrow starts with the shared electrons, goes to the Br. All right. Draw me a mechanism for that reaction. All right, so I'm going to go through this. This is the reverse. All right, the reaction on the middle board here that I just drew is called an elimination reaction. It's one of the two reaction types we're going to see in Chapter 7. And then each of those types is subdivided into two more subtypes. So this is an elimination. And really, if you look at this, we have eliminated. So above, the reaction you guys saw in Chapter 8 is called an addition reaction. We take the H and the Br, we add them to the alkene. Normally, in organic chemistry, everything is viewed from the perspective of the organic molecule. Like sometimes there are two organic molecules, but a lot, if I take an organic molecule and I do something with some inorganic thing, then I'm going to call it, like I'm going to name the reaction whatever it is from the point of view of the organic, right? I'm an organic chemist, I care about the carbons. Right? So down here, this is an elimination. We take the HBr and we take them off. And these are truly the reverse of one another. And so where the equilibrium lies depends on the conditions. And we can get into that. So entropy is going to favor the right here, right? 2 molecules versus 1. So entropy has a temperature. You multiply the change in entropy by the temperature to get free energy change. So at higher temperatures, we'll tend to favor elimination. The other thing you can do here is if there's a base, right? If we have a base in the system, the base can react with HBr, right? The elimination reaction produces a strong acid. So if you put a base in there to soak up that strong acid, you'll tend to shift the reaction toward the elimination. Anytime there's a thermodynamic principle, it's called the principle of microscopic reversibility. The reverse of a reaction has to happen by the same mechanism. It has to go through the same intermediates, right? Because if it didn't, it's like taking stairs, right? If I take the stairs up to my office and there are 12 stairs there, when I come down, right, if it's the same stairwell, I'd better hit 12 stairs or something's badly off with gravity. In energetic terms, right, if you imagine an equilibrium, if the reaction to the right goes through one intermediate that's got some stability, and it comes back through some other intermediate, and that other intermediate had a different stability, right, I'd either be creating or destroying energy. And the universe doesn't let us do that. So we know, you know based on that, this intermediate has to form here. All right, we have to form that same cation. And so now this winds up just being like that one problem on the exam and in that worksheet, right? You've got your structures here. How do I go from this structure to there? I'll let you look at your mechanism for a couple of seconds, see if you want to change anything. So now this is an elementary step. I'm going to have a set of curved arrows that take me from the starting point to the intermediate. All right, that curved arrow is just going to be the bromide leaving. The bromide is going to take its 2 electrons and go away. This gives us some terminology. So in Chapter 7, Br minus is going to be called a leaving group. And you already know this, you should know, right, that the carbon-bromine bond is polar. The bromine's partial negative, the carbon's partial positive. You also know that these bonds vibrate, right? So the carbon-bromine bond is always vibrating. Gets a little energy, it does a long vibration, and maybe it gets far enough away that the bromine just takes the electrons and flies off into space, right? Again, I talk about molecules like they're my friends and people I talk to socially. You can read into that whatever you want, right? But they're not. That bromine's not consciously thinking, I'm tired of being on this carbon. It's just, it's vibrating, it gets enough energy. Once it gets this far away, it's as energetically feasible to just keep flying off as it is to come back. Leaving groups, every reaction we see in chapter 7 is going to have a leaving group. Okay, leaving groups in chapter 7 are going to be chlorine minus, bromine minus, iodine minus, and then sulfonate esters. And I'll talk about these more in a bit. These are all going to be weak bases. All right? The leaving group, once it's left, has to be a weak base. I have to remind myself sometimes that I can talk faster than you can write. A few looks that kind of looked like, yeah, you remember this in April. Where were you in February? All right, so leaving group leaves. It has to be a weak base. So for example, OH minus is not a leaving group in chapter 7. Hydroxide never just like pulls off the carbon and becomes, or sorry, OH doesn't just pull off a carbon and become hydroxide. All right, so our curved arrow is just the CBr shared electrons leaving to give a carbocation and a bromide. And now here we have Br minus. We need to make HBr. We got a Br, we got an H. And now remember what I said over here about stabilizing a carbocation, right? The carbocation is stabilized by interacting with these bonding electrons around it. In this case, that would be these bonding electrons. In addition, you know, there's bonding electrons here and here, and there's two H's here, but I'm just going to use one hydrogen as an example. All right, so the CH bonding electrons here are interacting with this carbocation. That makes this hydrogen a lot more acidic. Right? The electrons that hydrogen's sharing with the carbon it's on are also being used to stabilize a cation. So that hydrogen doesn't have as much access to that, right? All right, so the next arrow, and you can think about this just in terms of what you need to do. I need to make a BR-H bond, and I need to make a carbon-carbon pi bond, and I need to neutralize this positive charge. So bromide brings the electrons, grabs the H. Now the CH electrons, this is an acid-base reaction. In the past, what you guys have done with just a Bronsted acid-base proton transfer is take the H whatever electrons and just make a negative charge, or a lone pair. Here, instead of making a lone pair, make the pi bond. And there you go. That gets your molecule. Not again. Come on, guys. We've complained about this. The housekeeping crew, and I mean, to be fair to them, I think people come and like see how well they're doing. And so they want to make this board like shiny clean. So they put like an oil on it or something. It looks really shiny and clean, but then you can't erase anything. All right. So like I said, that's an elimination reaction, and I'm going to write this, I don't think it's going to mean anything to you right now, but I want you to have it in your notes. All right. This is an E1 mechanism. Like I said, there's 4 reaction types, or there's 2 reaction types. Each of those has 2 subtypes in chapter 7. So in Chapter 7, every one of these reactions, SN1, SN2, E1, E2, are going to involve a base, or we might call it a nucleophile, and an sp3 carbon bonded to a leaving group. So I've given you a leaving group over there. The other terms here, we've got a nucleophile, right? A nucleophile is something that's looking for a nucleus. Nuclei are positively charged, so something that's looking for a nucleus is going to have electrons. It's going to be a Lewis base, electron donor. An electrophile is looking for electrons. Right? So it's going to be positive or partial positive. Right? The leaving group again, has to be a weak base. So once that leaving group leaves with its electrons, and that's always going to happen in all of these reactions, this is a curved arrow that's going to be there. All right? Depending on which reaction it is, that curved arrow where the leaving group takes its electrons and goes could be its own step, or it could be part of another step. But that has to happen in every one of these reactions. All right, so from here on out, I'm going to write NU or NUC. And I'm just going to take an example here. So I've shown you an elimination reaction. This is going to be a substitution reaction. Bless you. I'll show a general elimination schematic again here in a minute. Question? Dan? Yeah. Okay. So the substitution reaction, so this is the second of the two types in Chapter 7. One is elimination. In the elimination reaction, you're going to lose the leaving group. Okay, again, all the Chapter 7 reactions, you're going to lose the leaving group. And if there's no leaving group, if you look at a molecule, you say, there's no leaving group here. No Chapter 7 reaction can happen. Right? So if you just have octane, octane is not going to do any Chapter 7 chemistry. All right, so in the elimination reaction, the leaving group's going to leave, but we're also going to lose a hydrogen on a carbon bonded to the carbon that had the leaving group. I'll give you better terminology for that here in a minute. And you're going to make an alkene, okay? Elimination reactions are going to make carbon-carbon double bonds. That's going to be your biggest clue that the reaction is an elimination reaction. If I give you a reaction and there's a double bond there, that's an elimination reaction. In a substitution reaction, the carbon framework isn't going to change. But there's going to be a substitution. Right? Whatever the Lewis base in the reaction is, the nucleophile, the base, the thing bringing electrons, it's going to swap out for the leaving group. All right? So the nucleophile is going to make a bond to the carbon the leaving group's on, and the leaving group's going to leave. Make sense? There are two ways for this to happen. I know this board's getting messy, sorry. I should say that there are actually three, If you just think about this logically, so as if you knew nothing about how atoms bond, there are three possible ways for this reaction to go. The nucleophile could displace the leaving group in a single step. Nucleophile carbon bond forms, carbon leaving group bond breaks. You don't have to write this down right now. I'm going to draw some stuff here in a minute. Right, that's one possibility. All the bonds that form and break happen at the same time. Second possibility would be kind of what we showed over there. The leaving group leaves. You get a carbocation. Then the nucleophile comes in, makes the bond. Right? That's the third purely logical possibility is that the nucleophile makes the bond to carbon, and then the leaving group leaves. All right? Logically, that works. Chemically, for carbon, it doesn't work. Right? The nucleophile can't make a bond to that carbon because then the carbon's going to have 5 bonds. I only introduce that possibility at this point as you go down the periodic table. So if we do this chemistry with silicon, right, if this same reaction were happening but this atom right here was a silicon, that can happen. Silicon can make 5 bonds. So the nucleophile can make a bond to the silicon, and then the leaving group could leave. For carbon, that can't happen. So we've only got 2 possibilities. One is this one, and I'm going to draw the curved arrow for it. One single step. And then down below, while you're writing that, I'll write this other possibility. All right, so the second possibility is leaving group leaves, gives us a carbocation and either a leaving group anion. The leaving group gets the electrons. If it was neutral here, it becomes a minus. If it was a plus, it becomes neutral. And then the nucleophile makes the bond. Right? If you look at what happens overall, we have to make a nucleophile carbon bond, and we have to break a carbon leaving group bond. So those 2 curved arrows have to be there regardless. They can either happen at the same time or at separate times. Yep.
Does it matter the compound stabilization for that one?
I'm just saying this is just like broad generalities. Question was, does it matter how stable the carbocation is? And the answer is yeah. Like in terms of which one happens, yes, very much it matters how stable the carbocation is, right? Like if this carbocation is super, super unstable, this mechanism is not very likely. The other thing is, a lot of this gets driven by the base, all right? Okay, I should stop and interject here. Chapter 7 is long, not because the general concepts are hard, but because figuring out which situation applies is hard. All right, SN1, SN2, E1, E2 are all pretty simple reactions to figure out. I'm not saying you have it right now. Like, they're not so simple that you could just, I can draw them on the board and you have it. But either any of those 4 reactions individually wouldn't take very long to learn. The trouble is they all fit this stereotype. That's not really a stereotype. They all fit this general schematic, right? Like you've got a base, you've got an sp3 carbon bonded to a leaving group. All 4 of those reactions fit that. So how do you tell which one happens, right? In chapter 8, in the addition reactions we just did, again, I'm not saying it's easy, but if there's H2 there, you know not to add bromine. Right? If the reagent is H2 and an alkene, you're not going to make a brominium ion. If you think about the hardest, well, I don't know what you thought was the hardest, but probably the hardest there was like X2 and ROH. Now, where does the ROH go? What's the stereochemistry? The more options there are, the harder it is to figure out what happens. It's I mean, that is true of a lot of different scenarios in life, right? The more options you have, the more you can sort of just turn yourself in knots trying to figure out what happens. When there's one option, life is easy. It's not necessarily fun, but it's easy. Okay, so now we need to do a little bit of kinetics. Let's look at I'm going to have to erase some stuff. Shoot. Okay, so for this reaction, I'm going to add the curved arrows in. What I want you to do right now is draw me a reaction energy diagram for this reaction. So again, we've got neutral. The left and the right are neutral, right? All the molecules are closed shell. They all have full octets. They're neutral. They're going to be fairly close in energy. And again, overall stability involves temperature. If I don't tell you the temperature, it's hard to figure this out. The right side is more disordered than the left side. So at higher temperature, the right side is going to be more stable. But I'm just going to kind of put R and P sort of in the same place here. And again, I think most people got this on the exam, but there are a few people, and I know it's right at the end, so maybe you're Russian, but right? Anything we draw on the board, any structures you draw on the board in a mechanism have to be a local minimum. They might be an absolute minimum, but they have to be at least a local minimum. So we have one I here. All right, so we have the reactant, we have the intermediate, we have the product. There seems to be a death theme to today's class. All right, so reactant, intermediate, product. And then the other thing, and I know this is confusing, because it's just not very well defined. So energy, I think, is, and I think you guys get this, less stable stuff at the top, more stable stuff at the bottom. So the intermediate's a carbocation. You got a carbon there that doesn't have a full octet. That's going to be really destabilizing. So that intermediate has to be higher on the chart than reactants or products. A handful of people on the test wanted to put like at the peak. This is the reactant. That's the intermediate, another peak for the product. It's the minimum. The peaks are transition states. That's the high energy place you have to get over. All right, and so we've done, up to now, we've done right? I've talked about thermodynamics a lot more than kinetics. Thermodynamics is just where the equilibrium lies. What side's favored? What's more stable? All right, so like I said, here I've drawn a really small delta G, and that delta G will change with temperature. So if I increase the temperature, I probably move those products lower because now entropy is a more important factor. If I cool the reaction, delta G goes for products probably goes, or this probably inverts. Okay, kinetics are there. All right, the difference in energy from the reactant to the transition state. The higher that hill, like if the reactant and the product are a mile apart, and I ask you, how long does it take to walk from the reactant to the product? Your first thought is, well, just how fast can I walk a mile? Like, you know, a lot of average folks, 20 minutes. Pretty decent hiking speed for an average, not an average 19-year-old, but an average human is like 20, or I was going to say 20 miles an hour. I live in a nice little fantasy world. It's like 3 miles an hour, 20-minute mile. But that sort of assumes you're not carrying a lot of weight, it's flat, you're not crossing any streams, right? If I just tell you you got to hike a mile, you need to ask a lot more questions before you tell me how fast you can do it. And one would be altitude. So, right, if R and P are a mile apart, but Mount Everest is between them, right, it's going to take a little longer to walk there. So the higher this transition state is, the higher energy, the highest energy that you have to achieve is for the reaction to happen, the slower it happens. So we get this energy of activation, EA, and EA involves a lot of factors, right? Molecules have to collide, they have to be in the right orientation, you have to break bonds. But the higher EA is, the slower the reaction. The slower the step. All right? And we've got an energy of activation in both of these. So EA in the first step and EA in the second step. Clearly, then, the first step here is slower, right? And that should make chemical sense to you guys. Sorry, I know people are still writing. I want you to see this. Make sure I'm on camera. I have this voicemail. Never mind. I'll just distract you guys. Yeah, I can take that off. I have texts. Get off the screen. All right. Yeah. Wonder if my life is blown up. I have 2 voicemails and like 5 texts. So that'll be fun. Maybe I'll get out of my meeting that's at 2 o'clock. That would be, there's a pretty high bar of personal tragedy I would take for that. So, okay. This step is a high bar. This step is a low bar. So the first step happens slower. The bigger the EA, the slower the step. So the first step is, we would call that the slow step. And in terms of determining how fast this reaction happens, this first step really determines it all. So slow step, rate determining step, either one of those are fine. And like I said, this should make chemical sense to you guys. This first step, which again, this is going to be the slow step, right? The bromide leaves. We take a neutral, closed shell, all the atoms have an octet molecule, and we break a bond, and we get a carbocation and a bromide ion. All right? That should kind of ring some bells that maybe that's not going to be super fast. In the second step, we go from a carbocation, molecule doesn't have a full octet, all the atoms don't have a full octet, and a bromide ion to, again, closed shell molecules, everybody's got a full octet, they're neutral. That's going to be pretty fast. I'm going to take, if you were here, or you watched the video, I wrote fast where the S looked like an R the other day. All right, so slow step, fast step. But how do we get a rate law? How do we know, how do we express the rate of each of those steps? And so here's the rule for an elementary step. And an elementary step, there have been some questions about this. still? An elementary step is like one step in a mechanism. And what we say is everything we show from this step, so from R to I, happens all at once. And then everything that we show happening from I to P happens all at once. So every time there's a change in the structure that results in a local minimum, that's a step. And so for any elementary step, the rate equals some reaction rate constant, little k, and that constant varies for every step. But just put it in there right now. Right? Any reactant that participates in that step has to figure, the concentration of that reactant has to figure in the rate law for the step. Whew. This is a meaty class. All right, so for any elementary step, we got two elementary steps here. In the slow step, the rate of the slow step that slow step only involves one reactant. Just the alkyl halide. What is that? 1, 2, 3, 4, 5. The pentyl bromide. That's the only reactant. So the rate law for the first step is the rate is going to equal some K times the concentration of that alkyl bromide. Okay? For the fast step, the rate is going to equal the concentration of the cation times the concentration of the bromide ion. And again, these Ks are different. There's not one K. Every reaction step has a different K. When we say the slow step, we're essentially saying that Ka is really, really small and Kb is really, really big. There's another, I'm not going to press this too far. There's another thing that falls out of this. For the overall rate law, like, I don't really care how fast I form this cation, and I can't really measure the concentration of the cation, right? It forms, it disappears. So that rate law over there using the cation is kind of wonky. The overall rate law, what I really care about is how fast do I go from the reactant to the product. That's really what I care about, right? If somebody's coming to my house, I don't care how fast they get to the grocery store on the way. I care when they arrive. All right, for that, any reagent or reactant or catalyst, anything that's going to participate in or before the slow step affects the overall rate, right? What also falls out of that is most often, and this is what I basically want you just to use this. There are some exceptions, but in general, anything that appears after the rate law just doesn't appear. Right? So if a reactant reacts only after the slow step, it doesn't show up in the rate law. All right, it doesn't matter. What matters is how fast the slow step happens. And after that, you don't learn anything. If there were steps downstream, that affected the rate, then it wouldn't be true that that's the rate determining step, right? The rate determining step determines the rate. So the overall rate law for this reaction I just put here, which is, this is an E1 elimination, right? The overall rate of the E1 elimination is that Ka times the concentration of the alkyl bromide. We call this a first order reaction because the rate is only dependent on one concentration of that alkyl halide. All right, the last thing for today. For the top reaction over here, okay, this top reaction over here, I want you to write me a rate law. I'll give you about 60 seconds. So just the top reaction, the thing I've circled here. What is the rate law for that? More phone calls. Okay, so how many steps are there in this reaction? There's one. The mechanism tells you there's one. I got to make a nucleophile carbon bond. This arrow takes care of that. I got to break the carbon leaving group bond. That arrow takes care of that. So if we're going to draw a reaction energy diagram, I realize I didn't ask you to do that. There's no intermediate. Right? Single step, no intermediate. It's just a hump. If it's a single step, that means it's one elementary step. Every reactant participating in or before the rate limiting step has to appear in the rate law. If there's one step, what is the rate limiting step? It's that step. I know it's obvious, and we're like 74.5 minutes into class, but yeah. If there's one step, that's the slow step. That's the rate limiting step. So the rate has to involve both of these. Right? It involves the nucleophile and the electrophile. This is called a second order reaction. And now the chemical sense of it involving both of them, there's one step, and they have to collide. They have to collide, we're going to see next time, in a particular orientation. All right, so they have to collide in a particular geometry. That's all going to be in K, like how do they have to collide? How hard is it for them to collide? But if you think about it, the first thing is they have to collide. So if I double the concentration of one of them, I double the rate at which they collide. If I double both, I square I go up by a factor of 4 the rate they collide. All right, okay, so this is an SN2 mechanism. Last thing of the day, substitution. The nucleophile drives the substitution. It's bimolecular. All right, so E1 is an elimination where the rate is unimolecular, first order. E2 is an elimination where it's bimolecular. SN2 is substitution where it's bimolecular. SN1 is a substitution where it's unimolecular. Those are the 4 reactions. Have a nice weekend. I've got office hours today and tomorrow. and I'll talk to you then. My office hours for next week will go up either later today or early tomorrow. You bet. See y'all.